Hello and welcome to the Ecomodernist channel live. I'm Carl Pauls, joined by Gabriel Ignetti, Chris Bergen, Bjorn Peters, who, if you forget, is a physicist and energy economist, and our guest today, Cannon Bryan. He's held executive management positions and served as an officer and director for private and public companies in Canada and the US. Cannon has considerable experience providing financial management services to clients in various industries. He's focused primarily on energy and natural resource industries. Cannon was co-founder of Neocorp, a company developing the largest niobium deposit in North America, Uranium Energy Corp, where he served as an officer until October 2007. UEC is a producer of ISR uranium in the US, and previously, Cannon was the senior financial analyst for LASIK Vision Corporation, which was the world's largest provider of laser refractive surgical services. Today, we're going to hear all about the Terrestrial Energy IMSR. Gabe, go ahead.
Yeah, how you doing, Cannon? Uh, I know this is a general science show, so I had to ask, just for novices in the audience who don't know what an MSR is, if you could tell us what a molten salt reactor is and a little bit about its advantages, and just a little, give us a little background.
Sure, thanks. Nice to be here. Thanks for inviting me onto the show. Uh, yes, I'm Cannon Bryan. I'm the Chief Financial Officer of Terrestrial Energy, and yes, our company is developing the integral molten salt reactor, or the IMSR. It is a version of a molten salt reactor. Molten salt reactor is an advanced nuclear reactor system. It was developed by the Americans during the Manhattan Project, first invented in 1949, I believe, and it was prototyped and tested in the 60s and 50s and 60s. And it's a very interesting reactor system, very, very different from conventional nuclear reactors that we have today. It is a high temperature system, just on the highest level. It is a high temperature system, which is very different from conventional nuclear power, which is low temperature. So conventional nuclear operates at around 300 degrees C, and it uses water as a coolant, which isn't that great at high temperature. And but molten salt reactors use salt, various different types of salt as the coolant, which is much better as a coolant. It has a much more capability of achieving high temperatures, which is more efficient for energy production. So the integral molten salt reactor, the Terrestrial Energy's design, developed by Dr. David LeBlanc, our Chief Technology Officer, it's based on actually the most famous reactor experiment of the molten salt reactor, which was called the Molten Salt Reactor Experiment. Very imaginative name. And so our design is based on that design. There are a number of key differences, but it has its origins in that very successful experiment that took place in Tennessee in the United States. And the key benefit here is that you have a system that can operate at high temperature, again, which is very helpful for efficient energy production. And that also means that it can operate at low pressure, which is also very different from conventional nuclear. Conventional nuclear power operates at very high pressure. We don't need to, I don't think you want to go into the reasons. I mean, we can if you want, but the point is high pressure systems require more safety features because you don't want radioactive materials under high pressure getting it out into the environment. So if you have a low pressure system, like the molten salt reactor, low pressure or no pressure, then those extremely complex and highly engineered and safety systems don't have to be there. Basically, you can have a perfectly safe reactor system without 3 or 4 massive containment domes made out of nuclear grade rebar. all of that goes away. So these safety features that are inherent in a molten salt reactor system actually translate into economic advantages. So terrestrial energy is a commercial concern. We're not a lab. We're not a scientific enterprise. We are a commercial company, and we've developed this reactor technology for commercial use. We're a for-profit corporation, and we expect this to be an economic success story as well as an ecological success story, because it will, by developing a low-cost energy system that's clean, we believe that we are developing something which is in terrifically high demand everywhere in the world, low-cost clean energy. Who doesn't want that, right? And so we intend to by making a low-cost clean energy system, make it low-cost clean energy, or make clean energy, period, accessible to a far broader constituency around the world that needs it. So that is the molten salt reactor and terrestrial energy in a nutshell, high level.
Gabe, you want to keep us rolling? I'm getting not many questions from the chat right now. I'm going to put the website for terrestrialenergy.com. Nice and simple, good search engine optimization. Check it out. A lot of information on there. I've been a terrific fan for many years, and I've absolutely benefited from your wisdom and participation here in Seattle politics. We had this attempt at speaking with my representative, Pramila Jayapal, and getting her to support nuclear energy. It didn't quite pan out, but all you can do is try.
We knew it was a long shot from the beginning. For those who don't know, Congresswoman Jayapal is a massive proponent of wind and solar, and particularly 100% wind and solar. So we were really going out on a limb on that one. Nevertheless, she gave us the time of day for a while, and we were able to make our case.
Something that I've noticed, just to continue on to that, that when we get in the room with politicians, some of them who are more open do start to ask, well, what kind of timelines, what budget estimates, what schedules can you deliver us for when these will be built? And wind and solar is definitely easy to write all that down and predict it, because we've been expanding those industries for so long. But on the other hand, nuclear companies tend to treat that as confidential information. Is there any way that you might see to loosening that and being able to provide legislators a little bit of planned deployment, etc.?
So yeah, it is a bit tricky because there are a number of different factors, including for some companies, commercial sensitivity of these types of disclosures. But I mean, we have been public about what our projected costs are and what our projected schedules are for construction and licensing. One of the factors that we're not able to project is when we'll have a customer. So Terrestrial Energy does not have a customer today. So that's critically important. Really, it's the starting gun, if you will, for when that construction schedule can begin. So as a company, I can say that Terrestrial Energy is the most deployment-ready advanced nuclear technology in the global market. So in other words, put us against our peers, and we were to have a customer in a site tomorrow, I would suggest that Terrestrial Energy could be on the ground conducting construction activities the soonest. So that's not to say necessarily that our construction schedule is the shortest. I mean, we have publicly stated that it's the first one will be about 6 years. We intend for the nth of a kind version to be much shorter, and to realize some schedule savings from because of the modularity of the design. But that's basically what we're looking at for the first one. Now, in terms of those customers, I mean, I can say a little bit about that, but not too much. We are in many. We have many serious discussions with many large industrial corporations around the world, and we're advancing them apace. I mean, people talk about when selling a nuclear reactor. You don't sell a nuclear reactor. It's a massively oversimplified statement to say that you have a commercial engagement with an industrial counterparty on the other side, and it takes months and years sometimes to, from the starting point, going through the massive process that a customer has to go through in order to de-risk this kind of a commitment for themselves. So it's a massive process, and we've been undergoing these processes with many industrial corporations for months and years, and we just have to keep doing that. But
Chris had a question.
Mm-hmm. Yeah.
Sorry about that. It took me a second to find my.
Oh, Chris, yes.
Yeah, I've got two quick questions. One, do you know when you get to your nth of a kind reactor, how long will it take to build? Probably, will it be one a month, one a week?
Well, that's a good question. I mean, the design, as I said just now, it's a modular design, so it's really designed to be amenable to this sort of assembly line manufacturing type construction for the reactor core. And the reactor core can be built in this factory, and then it can be shipped to the power plant site, unfueled, of course. And the idea is, well, this factory should be able to build so many of these reactor systems on a regular basis, 100 a month or whatever it is. So, I mean, we had a study done actually by a Fortune 100 company a few years ago about a theoretical factory, a conceptual design for a factory like this. And, the findings were pretty interesting, but they were highly conceptual, of course. But we were they were suggesting that it would be possible to build 100 a month, which would be astounding. Wow. I mean, that would be, I would say, if we did 1/10 of that, it would be astounding. That would be an extraordinary achievement. That's that. It's a bit far off in the future because we haven't done any serious engineering on the design of a factory of that nature at this point in time. But I mean, that would give your audience a little taste of what's possible.
And that's amazing.
These reactors are tiny. These reactors are tiny compared to what went up in Georgia recently, but still, 100 or 1,000 a month would be fantastic.
Well, I mean, let me just put it to you this way: the IMSR. Boeing airplanes are built in a factory like this. It's probably one of the biggest types of biggest factories in the world. And they put out a regular number of jet airplanes every month and every year. I don't know what that number is, but just to put it in context, a Boeing aircraft has, I believe, 200,000 parts or something like that. And, the IMSR has like less than 100. So the level of complexity between cranking out, Boeing aircraft on a regular basis and cranking out IMSRs on a regular basis, it's a completely different discussion.
Yeah, I've got a second question, a bit more philosophical. I think you can remember like 12, 15 years ago, before you were involved with Terrestrial, everyone was excited about the small modular reactor and the possibility of the thorium molten salt reactor. I understand you're using uranium, not thorium, which is cool, totally cool. But I remember thinking back like 15 years ago, by 2020, 2024, we should be able to have 4 or 5 companies each producing, multiple reactors a month, and we're not hitting that mark. Is that cause for concern? Where do you see that as just are not being realistic initially when we learned about the technology? Because I'm not a nuclear engineer.
Well, it has less to do with engineering and even with regulation than it does with finance, I would say, perhaps. But I think, at the beginning, we started the company. I can speak for ourselves. We started in 2013. We were one of the first ones. I think there were two other companies or three other companies at the time that were doing SMRs, and a couple of those no longer exist. But I think we were being aspirational. I mean, we were projecting what we hoped to achieve, and the reality is, it is a very complex process to bring any new technology to market, and you have to go through all the various stages of the valley of death, and hope that you can arrive on the other side in one piece, without missing too many appendages, and it's and we're going through that process, and it's a long process, and we've always had the capital that we've needed, not always at the right time, and it could always be faster. That there's no doubt about that. I mean, 10 years ago, if somebody gave us a $1 billion check, yeah, maybe it would have been faster. I don't think we would have even wanted to do it that way, because for various reasons. But that's capital for new technologies that nobody has ever heard of, and that is true of advanced nuclear technology. I mean, the vast majority of people, including investors, have just never conceived of this technology as something that's real. It's just sort of imaginary in their minds. But that's changed a lot over the last 10 years, and I would like to give Terrestrial Energy a little bit of laurels for helping to bring that awareness of this technology to capital markets. I think we've had a hand in doing that, and many others have as well. But it's a process where the investment community has to learn what this technology is and and its significance to the world, the significance of advanced nuclear technology to the climate crisis and to the energy system, the global energy system. They don't yet have that full understanding, that full appreciation of what it means yet. But as insiders, as experts, we do. We have a very good idea of what it is. So this is what you have, what they call in the finance world, an arbitrage opportunity. So when the initiated understand the massive value of something, and nobody else really does understand that value yet, there's a big disconnect between what it is and what it should be. And so we're still closing that gap very slowly for now, and I think that it will massively accelerate. It already is accelerating, and the crisis in Ukraine has helped with that, because it's made other energy alternatives less appealing, like natural gas, for example, much less appealing now.
Yeah.
Particularly in Europe. So it's a process. We have to go through a process, and it'll take longer than anybody thought, and longer than anybody wanted, but we will get there, and we will have a technology that will be tremendously impactful for climate and for deploying low-cost energy to places where they don't have low-cost energy today, and delivering low-cost clean energy to billions of people. That will happen. It'll be a 100-year process. It's not going to happen by 2030. That's a unicorn. That doesn't exist.
I think Bjorn had a question.
Yeah, actually two ones. I mean, I'm quite fascinated about the terrestrial energy story. Maybe you should tell a little bit about the fuel that you apply. So is it thorium? Is it uranium? What enrichment level? What type of salts are you using? Because that's probably something that many people would be interested in. And second, have you ever computed target costs for your ISMR model given series production?
Yeah, so I'll just remind the audience. I'm the financial officer of the company, so I'm not an engineer. I'm not a scientist. Don't have a technical background, so I can only answer these types of questions to a degree. and beyond that, then I become useless. But so in terms of fuel, I can talk a little bit about fuel. I know what our fuel supply chain looks like, and yes, we are indeed using a uranium fuel. It's a uranium tetrafluoride salt. That is actually the fuel and the coolant, right? So that is built into the molten salt reactor design, is that the fuel and the coolant can be one chemically, so uranium fluoride, uranium tetrafluoride salt. And we use an enrichment level for this fuel, which is within standard and accepted supply chains today for nuclear fuel, namely lower than 5% enrichment. So I guess for those on the call that don't know what we're talking about, uranium has to be enriched with its unstable radioactive isotope called uranium-235, which is different from the vast majority of uranium that you find in nature, which is uranium-232. You have to enrich the uranium-235 isotope concentration up to a certain level to get it to achieve a critical mass or a critical reaction. And our enrichment level is 5%, and there are various standards for enrichment levels, because if you enrich too much, then you could possibly have something that could be used, that could be weaponized. And of course, the world doesn't want that. So 5% is considered fuel grade for nuclear power plants, and that's what we're doing. Now, many of our competitors have designed advanced nuclear reactor systems that require enrichment levels higher than that. So the way that the classifications have been made is that there's something called low enriched uranium, or LEU, that's 20% enrichment or less, 20% U-235 enrichment or less. Then you have something called MEU, which is medium enriched uranium, which is, I believe that's 20% to maybe 70% or something. And then there's no commercial MEU available. It doesn't exist. And then there's high enriched uranium, and that's basically exclusively used for weapons. And that's typically above 90%, but technically I think it's above 70%. So, but within the LEU category, there's below 5%, which is the standard fuel, which is standard fuel supply chain that exists for all commercial nuclear power plants in the world. And then there's this weird area between 5% and 20%, which is called high assay LEU, or it now has a nickname. It's called HALEU. So we do not use HALEU. A lot of our competitors, in fact, every Generation 4 system that's being developed today is using HALEU as their fuel. Unfortunately, there is no commercial supply chain for HALEU. It doesn't exist. And so it will have to be developed. And some of you may be thinking, oh, that doesn't sound too onerous. Well, as a matter of fact, developing any new fuel form for nuclear is very, very onerous and tremendously costly. It will cost billions of dollars. Someone will have to invest in that. It won't be the government. It will have to be some private sector company. And then you have to qualify that fuel. It has to go through all the regulations. You have to develop treaties so that this fuel can go, travel through different countries and over different airspaces and whatnot. It's a tremendously complicated matter. And then you have to develop the shipping containers. That has to be regulated. I mean, it is a very complicated thing to qualify new fuel and develop a supply chain for it. We don't require that, so we believe we have a commercial advantage by not using this higher assay fuel.
Yeah, I was. Go ahead.
I think
Carl, we were going to say
So ask your question, and then we'll come back to target costs.
Yeah.
All right.
Yeah, I just wanted to state before I say anything that if we really want a really effective Green New Deal, that you guys should be, the government should be the customer. They should be they should fund all of this, before the private sector even gets involved. But I was going to ask you this. I mean, you're talking about a lot of reactors. How powerful are those reactors? I mean, how many? Let's put it in layman's terms. How many homes would one of these light up?
Mm-hmm. Yeah, good question. I'll answer that, and then I'll go back to the cost question. So our system is 440 megawatts thermal, right? So we can one reactor of ours can deliver 440 megawatts of thermal power. So in a power plant, like a coal plant or any kind of power plant, they generally produce heat. That heat is converted into electricity, and when you do that, you lose a lot of heat. There's waste heat that goes into the atmosphere, and you can't use that. So our system, including our system, so we lose about 50% of our heat goes into the atmosphere as waste heat, and so our electricity generation for our reactor is close to 200 megawatts electrical. So what does that mean? It means that if we were to build an electric power plant using our reactor, one reactor, it could power about 150,000 homes, provide power to 150,000 people, roughly.
Homes.
People, let's say people.
Okay.
150,000 people, or 150,000 to 200,000 people, and then depending on where in the world you live, some people use more energy than others, and so our standard design for a commercial power plant is actually meant to deliver both electric power and heat power. So it's designed to deliver electricity, but also to deliver thermal power for an industrial process. We call that cogeneration. So it means you're delivering electric power and thermal power at the same time. So our cogen facility has two reactors, two of our IMSR reactors, and one of them is delivering thermal power, 440 megawatts thermal, and the other one is delivering electric power, about 200 megawatts electrical. So we can do any kind of formulation for a power plant. We can do, of course, we can do strictly an electric power plant if that's what the customer desires. We can do a strictly thermal plant if it's for an industrial facility, and if that's what the customer desires. So we're working with large industrial corporations, all these various different types of combinations based on what they need for their particular application.
Could you just repeat the temperature of the salt when it's coming out of the reactor?
Yeah, so inside the reactor, the equilibrium temperature is 700 degrees C. The output salt, which is a solar salt, is 600 degrees C, and we can make steam pretty comfortably at 585 C. So those are the temperature numbers. And then in terms of cost, Bjorn, just to go back to your question, so I can give you some high level cost numbers. So we've worked out what we think it would cost to build a plant. Of course, there's many different formulations. So if we were to build, so the most expensive type of plant that we could build would be a dual plant. In other words, with two reactors, all producing all electricity. So an all electric plant, two reactors, it would be rated at about 400 megawatts electrical, roughly. And so the cost of that would be around $3 a watt for the capital costs of building that plant, so in energy terms, that's pretty good. That is competitive. Even, to build a gas plant would be much lower on a capital expenditure basis. They typically come in at less than $1 a watt. But what you have to consider is the operating costs, stretching 60 years into the future. So the operating costs for a natural gas plant might have a low capital cost, but the operating costs are huge and subject to massive fluctuation. So, it's all dependent on the cost of natural gas. And that's, I don't think I really need to explain the vagaries of that. But when you build an IMSR, you have the capital cost. It's relatively low at around $3 a watt compared to building anything else. But once it's built, you have an operating cost which is tremendously low and very, very stable and reliable. So those operating costs will not change, and they're very small compared to the total cost of building and operating, and ultimately decommissioning the plant and remediating the land and handling the waste. So when you take all of those costs all together, we make the claim that our nth of a kind reactor will achieve a levelized cost, that's what they call it, a levelized cost of electricity of below 5 cents a kilowatt hour, or $50 a megawatt hour if you prefer that measurement. So less than 5 cents a kilowatt hour. And that number is very, very competitive with any other form of energy, including renewables, including natural gas when it was in a low price environment, which it no longer is. Natural gas is now in a structurally high price environment, and it will likely remain in that structurally high price environment for quite some time, many, many years. So we were competitive with low price natural gas, but we utterly destroy high price natural gas. So yes, the whole purpose of the company, as I said before, is to be a commercial concern. And our goal right from the very beginning, from day one, was to make the cheapest form of energy in the entire global energy system, to compete head on with fossil fuels, except that we were delivering an energy source which was totally clean. So we believe we have done that now. After 10 years of design and engineering and licensing, we believe we have achieved that. We believe we have a product which will compete head on with the fossil fuel companies and delivering low cost, clean energy.
So, Chris, may I stress the importance of this price point, because it's actually competitive even against coal in Indonesia, in Malaysia, everywhere in Africa, even in South Africa, and that's so important because if we want to successfully decarbonize, we need, of course, emission-free energy sources, but as well they have to be cost competitive in countries without climate policies. And that's why it is so extremely important to do a strict design to cost approach in nuclear, because this is something, if you look into Central African countries, they don't have the opportunity to build a coal power plant because you need a train of coal every day, but there is no rails, or a ship full of coal every week, but there is no waterways. So their only way to catch up with industrialization and with prosperity and with our lifestyle, and that's what they desire, is actually to have a cheap source that doesn't require a very complex infrastructure so commodities being shipped around. And that's where I think nuclear energy will play an enormous role. Maybe I can advertise my scientific paper on the global renaissance of nuclear energy a little bit that I published I believe, in October or so.
Wonderful. We'll put that link in the chat. Go ahead and put it in the meeting chat, and I'll put it on the internet.
I will.
Wonderful. So, Chris, I think you had one question. I want to note for our audience, thank you so much for hitting us up with so many amazing questions. I've reordered them, and we've got about 7 questions. I want to get through all of the ones that our audience has posed so far. So, Chris, give us a quick one.
Mm-hmm. Yeah. Cannon mentioned the waste heat. I'm curious if there have been conversations at all about capturing that waste heat and having 2 simultaneous modes of income. You could have your industrial heat at 400 megawatts and maybe 50 or 80 megawatts of electricity off the waste heat. So you have simultaneous incomes. Have you heard any conversations about that?
We have no plans to monetize or commercialize the waste heat. We can, however, if we have a cogeneration facility, it's so likely, in fact, that we built it into our plan that we would deliver thermal power and electric power, but that if there would be any excess power, in other words, power above and beyond what the industrial facility needed, that we could sell that excess power to the grid, and always make sure that we are monetizing every last kilowatt hour that comes out of the plant.
So here's our audience questions. The first, welcome Sandy from Environmental Coffee House. The Environmental Coffee House program is where we hear a little bit of the climate, not skeptical, but the climate fearful group. And so we will acknowledge that climate is a big and scary thing. But here on the Ecomodernist show, we absolutely think we have answers to those problems. Sandy asks, where are these critical minerals coming from? And I might add, where would the fuel be developed?
Sorry, is that for me?
Yes.
Mm-hmm.
And as much as you can tell us, and Gabe and I might fill in.
Well, I mean, the critical materials to build the power plant, for example, is that what you think they mean? I mean, as a matter of fact, before I did nuclear, I was in the mining business. I was an analyst, a financial analyst in the mining industry. So I know a thing or two about this. I also developed mining companies as an entrepreneur. So, I mean, in a general sense, what I can tell you is that the primary materials that we use in our industrial economy every day, those minerals exist everywhere in the world, all throughout the Earth's crust, even in the oceans. And there's a difference between where they exist and where they are actually being extracted. They're being extracted in places, typically concentrated in certain places, not always where we want them to be. So, for example, some people may know about this. The lanthanide group of metals, nicknamed the rare earth elements, they are by and large mined in China. And as I believe Bjorn just pointed out recently, not all places in the world have environmental law or environmental regulations, and so they're allowed to have mining practices which are not particularly good for the environment, and so we don't like that. We don't particularly want them to do that, but that's our political and economic reality today. And so that's not to say that these minerals couldn't be mined somewhere else. I mean, of course they can. It's just a question of can they be extracted economically, and does the technology exist to be able to refine those materials, beneficiate them in such a way that they can be used for industrial purposes. With respect to integral molten salt reactor, our design, it does not use any exotic materials that are not broadly available in virtually every part of the world. So, we use steel, we use concrete. These are, of course, we use uranium fuel, which which is abundantly available in the global market. Though it too is quite concentrated. The production of uranium is concentrated in places like Canada and Russia, and there's a lot of the largest producer is Kazakhstan, which is controlled by Moscow, unfortunately. So that's not very convenient. But there are other large producers of uranium and around the world, and uranium, again, like I just finished saying a couple of minutes ago, it's available everywhere throughout the Earth's crust. I mean, it's in higher concentrations in some places more than others, like Canada, for example, where we have very, very high grade deposits. So, I mean,
I'd like to hear a little more about Canada's uranium industry. It's nothing like what they have in Kazakhstan. Of course, Kazakhstan basically has these loose sands with their uranium, where it's pretty easy to extract. Canada, it is mined, and I understand Canada is a pretty pro-labor environment. Is safe for the workers? Is it, environmentally responsible?
Canada has the most stringent environmental regulations for mining anywhere in the world. All other countries that do mining that have an environmental conscience, they aspire to have regulations as stringent as they do in Canada. U.S. is pretty good too, but Canada is a world gold standard. Yes, all of those things that you just mentioned, worker safety and everything else, are at the highest level possible.
We've got many more questions, so I'm going to go through a few of these. David Tremaine on LinkedIn asks, where, when, and how are these supply chains developed? And how do they bring security into the process for mass production?
Supply chains for fuels or for exotic materials, or
moving into general construction, I'd say. So moving into like where you're going to have a factory for your primary heat delivery mechanism. And I assume you have different supply chains for the rest of the mechanism and modules involved.
Yeah, so I mean, our power plant. I can speak to our power plant. That's what I know a little bit about. We have three main components. We've got the reactor core, which includes everything that's radioactive in the entire power plant, which is very unique. That's a very unique thing for a nuclear power plant. Then we have the reactor, or the nuclear island, so-called, which is really just a building. It's a concrete box. There's nothing really that unique about it. And then we have if we're making electric power, if we're converting our heat to electricity, then we have the power conversion systems. So that's your steam generators, your turbines, those types of things. And I mean, for our power plant, the balance of plant infrastructure is all very standard. So all those supply chains already exist. We're not creating anything new. Some of our competitors conventional nuclear power plants, they do require special supply chains for that because they have radioactive material going through some of their balance of plant. So that has to answer to a higher standard. But in terms of the reactor core itself, probably the most I could put it this way: the supply chain which has to be created that doesn't really exist today is for our graphite moderator. So graphite was extensively used in the UK it still is actually for conventional nuclear power plants. We need to have a stable supply of graphite moderator if we want to have a massive deployment of power plants. So that would probably be the thing that needs to be created that doesn't exist today. But it's not difficult, and it doesn't rely on natural resources. The graphite that we use in our system is nuclear grade graphite. It's manufactured, so it's not mined out of the earth. I realize that you can mine graphite out of the earth and use it for industrial needs. We can't use that graphite because it's not nuclear grade. So ours has to be manufactured and fabricated in a plant. So we will create our supply chain for our graphite moderator. And I mean, the other things that go into it, yes, the uranium, we've already discussed that. There's a stable supply chain for that. In fact, we already have our supply chain suppliers that are going to be supplying that fuel to us under contract. And they're big names in the nuclear industry. You have the salts, which, again, I think somebody asked me what salts are using. I can't exactly tell you, but I can tell you what we're not using. We are not using some of the more difficult elements that are used in some of the molten salt reactors today. We do not use lithium, which is a big stinker. It's a troublemaker. And we do not use beryllium. That's another one of these strange materials. So, our salt is, I think I can safely say, is free from any controversial materials that might be going into it. That's just the way our system was designed. Everything, virtually everything else is steel. There might be some alloys that we need to employ into like the heat exchanger system, for example. But there's nothing exotic here. So we don't anticipate, with the exception of the graphite, we don't anticipate having to create all of these new supply chains. And again, this is one of the fundamental philosophies of the whole company right from day one, to build a system which is low cost, simple to build, accepted, which has established supply chains and an established regulatory pathway. All of these things create a pathway to market that is accelerated and gets us to the market as quickly as possible.
Go ahead, Gabe.
Yeah, how user-friendly is it as far as operations go?
Well, I've never operated one, but I can tell you one anecdote that might help to answer your question. The manager of the molten salt reactor experiment, which happened at the Oak Ridge National Laboratory in Oak Ridge, Tennessee, in the 1960s, the manager of that project, very nice man by the name of Dick Engel, or Richard Engel, Dick Engel. And Dick Engel was, he passed away a few years ago, but he worked as an advisor for Terrestrial Energy for the first few years, and he was provided invaluable pearls of wisdom about the molten salt reactor experiment, its design and operation, and so forth. And he's deeply missed now. But the one thing that he always said that I'll never forget, which is that operating the molten salt reactor experiment was the most boring job in the world, because he never had to do anything. It just did it. It just operated. It's just basically sitting there watching, measurement gauges and whatnot. And I've heard that, we have people in our company that were in the U.S. Navy submarine programs, and they basically tell me the exact same thing. They were reactor operators on these nuclear submarines, and it was the most boring job in the Navy because nothing ever happened. They never had to do anything. They just sat there and watched the reactor just operate, sort of on its own. There wasn't anything to do. So I think that should give you some sense of what it would be like to operate an IMSR. We obviously haven't built one yet, so we don't know, but for sure. But a pretty good, strong sense from various anecdotes on these things that it's going to be very user friendly.
Yeah, and actually, this is something that holds for every reactor with liquid fuel. I mean, it's using very basic, even geometrical. So it's not only physics. So it's more fundamental than physics. That it's a self-controlling engine. So there is nothing to control in these reactors or in this class of reactors. The only parameter actually that determines the speed of the fission reaction is the amount of energy you extract. And that's very interesting because it creates an analog computer, so to speak, which is always in balance. And the only thing is you need to come up with a good purpose for that reactor. But everything else in it is self-controlling. And that's a very fundamental improvement, I believe, over light water reactors. I mean, they are extremely safe and very, very, very well designed nowadays, the EPR and the AP1000. And so, and the Hualong and even the Russian VVER, I mean, they're really, really good reactors, but they rely on technology to control the fission reaction. Whereas all those models that use liquid fuel, they use physics and very elementary physics to control the reaction. And that's a very strong statement, actually, for the use cases. That means you can put them in the middle of industrial centers, and so directly within a chemical within a chemical plant to produce ammonia or hydrogen or other base chemicals, ethylene. And that's a very fundamental difference in use cases. So the traditional large-scale power plants usually are located somewhere very much outside of the big towns, and the only ones that did this differently were the Russians, where they're actually using cogeneration. But in the West, this has never been a valid concept, with I believe only one exception somewhere in the US. But so this is very fundamental, and so it's good to have those liquid fuel reactors around.
Mm-hmm. Yeah, Bjorn, you're absolutely right. And I wish you were the CEO of a super major oil company, and just to have this level of understanding, because
I am the CFO, so I'm actually a colleague of a nuclear company, but we are not as far as you are. We're at Dual Fluid Energy in Vancouver.
Oh yes, I've heard of it.
Yeah.
Wonderful. So the next question we've got from Kenjing Henan, aka Clean Nuclear Energy in China. Do you need to build a prototype reactor for regulation review?
Is this one for me as well?
Yes.
Okay. So we do not. There were prototypes of the molten salt reactor that were built and operated, again, by the Americans. We discussed that a little bit. And so we don't believe as a company that we need to take that intermediary step. We would prefer to just build a commercial power plant as our first build. Now, for regulatory purposes, it is incumbent on us to prove to the regulator that the reactor works and that it's safe. And so what we are not allowed to do is we're not allowed to take the results from an experiment that happened 60 years ago and say, here you go. It doesn't work that way. So in a lot of cases, we have to recreate bits and pieces of the molten salt reactor experiment. And we have to present those newly created results, which mirror, the historical results, and show that to the regulator. The fact that there are historical results is very helpful, so we can compare our results against the historical results, and if they match up, then that's extremely helpful. And then yet again, those will match up against the computer simulated models of those experiments. So you really have all of this double and triple reaffirmation of all of these experimental results, and you can show that to the regulator, and then they can have some comfort that it's operating in a way that is predictable and safe. Of course, it has to be safe. So no prototypes, but we do have to recreate most of the elements of those early prototypes that were built and that were operated in bits and pieces. So we've got pieces that are being done in labs in Europe, and then we've got pieces that are being done in labs in North America, and so it's sort of piecemeal all over the place. But I mean, if you put them all together and consolidate them, would probably almost equal a molten salt reactor experiment.
Gabe, go ahead, and we've got about 5 more online questions.
Yeah, I know you wouldn't need a prototype. I could accept that, but like anything that's built, you would have bugs, and you might find better ways of doing it in the process of doing it. So how long would it take to kind of work through that? Would you? I mean, it's a speculative question, but how long would it take before you'd feel comfortable, mass producing these?
Yeah, that's not a Canon question for sure. You can ask our engineering team, but they may know, they may not know that. But no, I'm sorry. That is beyond my capability of answering.
Okay.
So we've got a question from David Tremaine, and I think this one's U.S. centric, so I'm going to rephrase a little bit. Are there practical ways to access government funding? Is there a way that you can secure sort of government assistance or financing for long time periods of development, like your first reactor plant being a 6-year project?
Well, the answer is yes. I mean, especially now with the bipartisan infrastructure law and the Inflation Reduction Act, the cone of opportunities for grant funding has just exploded. I mean, it's just massively increased. So, terrestrial energy, I can speak to our own experience. We've had success in raising grant funding from the Canadian government, the U.S. government, and state and provincial governments. We've also successfully applied for a $1.2 billion loan guarantee from the U.S. DOE Loan Programs Office under Title 17 of the Energy Policy Act of 2005. So, I mean, if we can do it, I would suggest that anybody can do it. Most, if not all, of our peers in the industry developing advanced nuclear reactor technology have all applied for grants and won grants. We've won numerous GAIN vouchers from the Idaho National Labs. I can rattle off a whole list of things that we've done that we've been successful in doing. We're going to continue to apply for grants as we carry forward through the final stages of the development project. In other words, to get it to the point of construction. And then as we approach the deployment phase, we would expect to use the loan guarantee to de-risk the capital risks that are inherent in project finance for building a new technology or new technology-based infrastructure. So, yeah, I mean, from my perspective, there are massive opportunities, and they're only increasing because nuclear is being recognized as a clean energy solution, as a clean energy technology, and so governments that are seeking to find solutions for climate change are providing much more funding to these types of technologies, and I think you can say that certainly for the US and Canada, North America, and for the EU and big parts of Asia as well. So I would say yes, that's definitely very possible, and almost I would say it's almost a foregone conclusion.
Wonderful. So from Sandy at Environmental Coffee House, could a plant like Indian Point in New York be converted to an IMSR?
Yes, absolutely.
Wow.
And any power plant that exists today or is decommissioned could potentially be a site for an IMSR. Now, I say that answer without regard to regulation. Okay, so I'm just strictly talking about the technical possibility of doing it. Now, once a nuclear power plant has been decommissioned is a technical regulatory term, and it has very specific meaning. And it's when you, in the regulatory sense, when you decommission a nuclear power plant, it's almost like frying an egg. You can't unfry that egg and make it back into a raw egg. That's what they say. But as it turns out, there is an example that exists today, right now. There's a power plant, a nuclear power plant, which has been decommissioned, and there's a private company in Michigan that is seeking to bring that power plant back from the dead and to operate it and to bring it back to life and to have it operate. And they're seeking for funding. They're seeking funding from the U.S. government, which is available for this specific purpose. And they want to put that nuclear power plant back into operation. So that is, I don't know if that's ever been done before. And I think the sense in the industry is that they're facing a bit of an uphill battle. But if the Biden administration is sincere about its desire to salvage these nuclear power plants that are being closed prematurely, then I would suggest that the Biden administration should command the Nuclear Regulatory Commission to help this private sector company to bring this power plant back to life. Because, I mean, it's just about moving papers around, really. I mean, that's what regulation is. I mean, they can either accept what this company is trying to do and accept that it's safe, or they can reject it. And it's all a matter of pieces of paper. And if you want to do something and there's a regulation or a law in the way, well, you just write a new regulation or you write a new law. I mean, that's the way it works. These are all constructs. And the only thing preventing them from carrying forward is a different construct that replaces it. So I wish that company success. I hope that nuclear power plant gets brought back to life. And I hope that is a trailblazer for other decommissioned nuclear power plants in the United States and elsewhere to be brought back to life after they've been decommissioned prematurely. Because to decommission a nuclear power plant prematurely is criminal, in my opinion. It is criminal. It causes emissions to increase. That is proven every single time that it happens. And it causes people to die unnecessarily. It does. It kills people. It kills people. You decommission a nuclear power plant before it's before the end of its useful life, and people die. So I don't understand how that can be justified. And bravo to the Biden administration for seeking to undo that injustice, and I hope that it can be put into operation.
Great. Chris, go ahead with your question.
Yeah, quick follow-on comment as well. I believe Cannon's right about decommissioned plants being, so far, they've all been permanent. But I believe Tennessee Valley had one that they started to build. They did not complete. It sat empty for over 2 decades, and then they came back and finished it and went online, about a year and a half ago, I believe. So it's a similar kind of a thing there where they went back to it and finished it and turned it on. Anyway, my question, Cannon mentioned that nuclear has become very popular, especially since Russia made the poor choice to invade Ukraine. But I'm curious if you know some famous politicians or movie actors, whoever, Pulitzer Prize winning writers or something, who used to be anti-nuclear or on the fence, and they've come up pro-nuclear. I know John Kerry is one of those people who's currently a private envoy for the U.S. But do you know some other people you could just mention offhand?
Gosh, I would maybe question your assessment of nuclear as being very popular. I think it's less unpopular than it was than it was 2 years ago or 5 years ago, 10 years ago. But to answer your question, yes, there have been a number of high-profile people or celebrities, if you will, that appear to have changed their position on nuclear energy recently, and that's helpful. I think if politicians have or celebrities have influence over other people or over the way laws are made, then that's helpful. I think from my perspective, the people that you really want to convince are the technical experts, and because those are the people that really understand what's going on, like the scientific foundation of what's happening. And so those are the people that really need to be convinced. As far as I know, most people in the scientific community believe that nuclear power is a force for good, except for people in Germany. Present company included, Bjorn. But German scientists seem to have, I don't know, they seem to have gone on a field trip somewhere to to another planet. But most scientists and engineers, I think, are it's pretty consensus view have a pretty consensus view that nuclear energy is an engine for good and an engine for climate change mitigation and so forth. So those are the people that I really care about. And if you want one example of a celebrity that has embraced nuclear energy, it just so happens that I'm reading the autobiography of Bono, famous rock star Bono, right now, and it turns out his wife is very anti-nuclear, but Bono himself is very pro-nuclear because he's good friends with Bill Gates, and Bill Gates is, of course, one of the most high-profile proponents of nuclear energy and nuclear technology in the world, and so he's convinced Bono of something that Bill Gates views as obvious, which is that nuclear energy is an engine for good. So there you go. You have a house divided in Ireland.
I'll also compliment, we have got some really great people who have stepped up their advocacy, and I'd like to compliment Mark Linus for doing some great work and advocating with Replanet. The Replanet is the European Ecomodernist group. They're doing some really amazing work. So yeah, hats off to folks like Mark Linus, who are turning the corner in their advocacy and really helping bring us together. Let's go for another question from Sandy. Can you tell us about the waste cycle for the IMSR? What's your plan?
I'm going to decline to answer that question because I'm a financial officer of the company, and I don't like getting yanked into discussions about waste. We do have a plan, and we have a contract with the Nuclear Waste Management Organization, and we're working with the Australian Nuclear Science and Technology Organization, or ANSTO, that has a waste technology that we seek to employ. But yeah, it's beyond that. I don't prefer to get into any more detail on that subject.
So if I can guess, I will guess a couple of things. NWMO has a deep geologic repository plan, and ANSTO already has repositories for medical waste and other. They produce in Australia they produce a huge amount of irradiated silicon for semiconductors, and so they're managing that waste as well. So you're connected with the experts, global experts in waste management, and geologic repositories are good enough for arsenic in Germany. So why not used fuel? Our final online question, Sandy asks, will a warming climate impact how your reactors function?
Probably not, but I believe that if anything, it could make them more efficient. Because if you, I don't think I know enough about the subject to speak intelligently about that.
Yeah, I'll fill in a little bit.
Maybe I can.
Yeah, go ahead, Bjorn.
As a tiny little bit. The thing is that with cooling, so you need some sort of cooling. It's a thermal power plant, and it is not driven by temperature, but by temperature difference. So you need a basin of cooling in order to get the so-called exergy. That is the difference between the energy levels from high to low. The higher the temperature of the power plant, the more likely it is that you can work with air cooling. So at 585 degrees, it's more. It's not as efficient as having a water cooling doing it with air cooling, but it is still feasible. So you lose a couple of % of efficiency rate, but it's compared to every other alternative. And in mid-Africa, in Timbuktu, so if you would build a terrestrial energy power plant, an IMSR in Timbuktu. There's no water there, but even with air cooling on the day when it's 60 degrees, maybe Celsius, I don't know. I mean, I've never been there. So it would still be much better than the alternative of having no energy at all.
Mm-hmm.
Oh, yes.
And a quick follow on, if I could, I believe if the salt cools too much, like falling below 200 degrees Celsius or 140 degrees Celsius, depending on the salt composition, if it cools off too much, it becomes a solid, and that becomes a huge problem. So you want it to cool moderately, but not too much. And so that's something that the technical people would work on under a variety of situations to study beforehand to make sure that it'll operate in the wintertime and on the summertime.
Yeah.
Cool.
Well, we have gone about 70 minutes so far. Thank you so much, Cannon, for sticking with us. Do you want to spend another 10, 20 minutes and have some fun questions?
Actually, I have a serious question. I would be very much interested. I mean, at 585 degrees, you can do, and that's actually a question for the CFO, because you can do a lot of interesting chemistry that works very well at let's say 600 degrees, and it's at least better than with 400 degrees, which is the typical light water reactor output. Is there any plans around what you could do precisely with that type of energy of heat at 600 degrees? And do you have plans to commercialize on this?
So all I can say is this: Terrestrial Energy and the U.S. Department of Energy did a lot of work over the years on looking at what type of industrial facilities in the United States were amenable to the character of power that we were able to produce with our IMSR. So we did a big study and looked at 2,000 industrial facilities in the United States, which is virtually all of them. And what they found out was that our character of heat and power was suitable for over 80% of all the industrial facilities in the United States. I think we've subsequently figured out that it's maybe closer to 60, but hey, that is still a massive number. So the type of industrial facilities that would work well with our character of power, I mean, they're legion. They are chemical processing facilities, fertilizer production facilities, I mean, all types of metal smelting and things of that nature, food production. I mean, I could really, pulp and paper, I could go on all day here. I mean, we all know there are thousands of industrial applications out there in the world that make the products that we use every single day. So the good news is, because of the character of our power, we can service the majority of those facilities, which means that it also means that we can eliminate the emissions associated with those industrial facilities, because those industrial facilities today are using fossil fuels, every single one of them, and they have been since the dawn of the Industrial Revolution. So this represents a total sea change in industry. The way that industry gets its power is going to totally change thanks to these types of technologies, and including the IMSR.
That was amazing. I actually, you know what, I really want to keep this program positive. You've had such a great time, and I want to let's not rile anyone up today. Though we did kind of behind the scenes grouse about Earth Day, and so let's turn a page and everyone come together. We want to focus on climate solutions and not so much our divisions. So we're going to keep this show about positive solutions and talk about how we really think that we can deliver something to the world as nuclear advocates, as Cannon and his entrepreneurship has brought us this opportunity, working within the system that we live in. We're not going to wait for the revolution to solve climate. So, Cannon, you've brought us the next best thing, and thank you so much for answering our questions today.
Thanks. It was my pleasure. It was fun. So
wonderful. Any final thoughts, anyone? Okay. Well, thank you so much. I'll go ahead and close it out. Go ahead if you've got anything.
I was just going to say I enjoyed meeting you, Bjorn, and hope we can connect at some point in the future.
Yeah, that would be a great pleasure. Actually, are you going to the SMR conference in Atlanta? Next, it's.
I might.
I'll be there, and it would be great fun meeting you. So I was enjoying this conversation very much as well.
Yeah, me too.
Wonderful. So thank you, everyone. This has been the Ecomodernist channel live. You can watch us here every Sunday, or almost every Sunday at 11 a.m. Pacific, 2 p.m. Eastern on the Ecomodernist channel on YouTube. You can also catch us at Soyaddle, that's Seattle without the C and add in the soy, here on twitch.tv. As well, I've got Thorium252 on DLive, I've got Soyaddle on Kick, and a few other thorium-based names, various broadcasting channels all over the internet. Join us again every Sunday, 2 p.m. Eastern, 11 a.m. Pacific. And remember, emissions first, peace and justice will follow.
I want to speak to you about a new organization called the Ecomodernist Society of North America. I'm here because we are in the midst of a potentially monumental ecological crisis. It is only through a new environmentalism 2.0 that progress can be made. We believe that our only hope for human advancement and even human survival is through the exponential advance of science in the service of humanity. Ecomodernism is a new environmental paradigm which looks to reverse the fear of nuclear power and scientific progress in general. Ecology-based modernism is the most direct way to define it. Ecomodernism as a philosophy is described in the Ecomodernist Manifesto. We believe humanity should not be rejecting technological progress, but rather separate our impacts from nature through the responsible use of technology and urbanization. Urbanization is an unstoppable worldwide trend and the best solution to many environmental problems. It offers sustainable development for the human population and is a historic antidote to both deforestation and species extinction.